Hi, welcome to class 7 of this crash course series. In this today's session, we are going to discuss about solution and colligative properties. Today, we are going to discuss about the weightage of the concepts, how many marks can be asked from which concept, and we are going to do the revision of entire chapter. We are going to play with the formulas, how to derive, and what is the usage of derived formulas, and finally we are going to solve some previous year questions. In this particular chapter, you can expect more amount of numericals than the theory question, because this chapter comes under physical chemistry. Physical chemistry, that is more aligned towards numericals, isn't it? So without any further delay, let's get started. Let's analyze the paper of past 10 years. From that 10 years of paper, I came to the conclusion the concentration terms, finding about molarity, molality, normality, ppm, which we covered in mole concept as well. That part you can expect the questions, which is 10 to 15% of questions. Then coming to the vapor pressure and Raoult's law, include the ideal and non-ideal solutions, positive deviation, negative deviations, and everything come together. You can expect a question. And solution thermodynamics, delta H, find delta G of mixing in case of solution, in case of non-ideal solutions. You can expect a question. And most importantly, the colligative properties. So colligative properties, lowering of vapor pressure, osmotic pressure, elevation in boiling point, depression in freezing point, 1/2 factor. From those important 5 formulas, you can expect a question. So that's about solution and colligative properties chapter. So let's start doing our revision. First of all, what is this chapter is about? It's about solutions, right? What is solution? Solution is made up of mixture of 2 or more substances. It can be of homogeneous mixture, it can be of heterogeneous mixture. We very well know about what is homogeneous, heterogeneous, right? So here we are talking about homogeneous mixture, which means that all the components are mixed, uniformly distributed throughout the solution, right? We know about solute, we know about solvent. Please be clear about these 2 terms, which is very important to proceed with this chapter. Okay? So mostly we will be talking about binary solutions here. Binary means 2 components in the solution, right? First of all, what are the types of matter? What are the different states of matter generally available here? That is solid, liquid and gases, right? Other than that, we do have other classifications of matter, but generally we are talking about those 3 states of matter. In that, we are going to prepare a solution using any 2 of those states of matter. That is what we are dealing with, types of solution. First of all, let's start with gases. Gases in gases. The simple example, that is air surrounded by us, the environmental air. O2 is there, N2 is there, some small amount of hydrogen is there, right? All together they are mixed and forming a homogeneous mixture. So that is an example for gases in gases. Solute also gas, solvent is also gas. Then gases in liquid. For example, oxygen in H2O. If I am taking a water bottle, half of water, the remaining is maybe consist of gases. Or if I am taking carbonated water, which is mixed with sweetened water with carbon dioxide gas, right? And third category, that is gas in solid. That is a famous catalyst which we use, palladium with hydrogen catalyst, right? Hydrogen in palladium. Then the fourth classification, that is liquid in liquid. The simple example would be ethanol in water. You don't know why. Then liquid in solid. In that category, you can expect amalgam, mercury amalgam, silver amalgam, and etc. Similarly, in solid in liquid, solid present in liquid, which is salt solution, sugar solution, just to think about the component and answer it accordingly. Okay. And finally, we have solid in solid. Alloys, right? Gold. We are mixing gold with copper. We are mixing gold with silver to prepare an alloy, to prepare a jewelry. So that is an example of, that is a type of solution of solid in solid. So talking about these kind of mixtures, we should talk about solubility. What is solubility? How much the solute can be dissolved in the solvent. That is the solubility of that solute, right? For example, if I can dissolve 20 grams of salt in 100 grams of water or 100 ml of water, then the solubility of salt is 20 grams. I just took it for example. Okay, so we talked about solubility. Then we are moving into factors affecting solubility. If I'm mixing any solution, if let's say I'm mixing sugar and water, what are the factors will affect it? Obviously, temperature will affect. In our home also, while preparing sugar solution for sweets, we increase the temperature so that it can dissolve better. Right? You can try out this example, how temperature affect the solubility. If that is an endothermic dissolution, if I'm supplying heat, the solubility increases with temperature. For example, the dissolution means the mixing process. If that is an exothermic process, then the solubility obviously decreases with temperature. We know why, because we dealt with equilibrium chapter also. Then effect of pressure. What happens if I am applying so much pressure? I am trying to mix solids in liquid, salt in water or sugar in water. What will happen if I am applying too much of pressure? Will that affect it? Obviously not. It won't be. If that is affecting also, it won't be considerable. It's not significant, right? It is negligible. For example, if I am mixing gases in liquid, the pressure will affect this type of dissolution. Yes, the pressure is considered as a very important factor in this kind of dissolution. How it affects? We can see that from Henry's law. Henry's law states that pressure is directly proportional to the mole fraction of the gas in a solution. Henry's law is for gases in liquids. So please be careful. Henry's law is for gases in liquid. In this chapter, we are going to see one more law. Okay, so don't get confused. Henry's law, you can remember it like Henry starts with H. You can remember that as a hydrogen or helium. So gases in liquids. Okay, don't get confused. Henry's law, which states that P is proportional to, the pressure is proportional to X, that is mole fraction of gases in solution. To remove that proportionality symbol, we are using the constant Kh, that is Henry's constant. So question can be asked involve Henry's law also. So please make sure that you are thorough with this formula. Secondly, will temperature affect the gases in liquids dissolution? What will happen if I am increasing or decreasing temperature in gases in liquid type of solution? Generally, it decreases with increase in temperature. Why? In case of exothermic process, the heat releases. So usually this type of gases in liquid follows exothermic process. In that case, if I am increasing the temperature, the solubility decreases. I'm going to talk about the next type of solution, that is liquid in liquid type. For example, ethanol in water or HCl in water. So you can take any example of liquid and liquid forming homogeneous mixture. So here the solubility is, you have to remember one thing while talking about solubility, that is like dissolves like. What is that, ma'am? Like dissolves like means if the solute is polar, it will dissolve in polar solvents. Like if a solute is non-polar, that will dissolve in non-polar solvent. So that is what, by the catchy mnemonic, that is like dissolve like. Okay, so while doing dissolution, you should keep in this mind. Okay, so talking about liquid and liquid solutions, there is a famous law which states about the pressures. That is Raoult's law. In gases and liquid, we talked about Henry's law, which states that it is proportional to, pressure is proportional to its mole fraction. That is Henry's law. Here, Raoult's law talking about partial vapor pressure. He states that for a solution of a volatile liquid, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction pressure in the solution. For example, if I am talking about the partial pressures of the surrounding air, the hydrogen will have certain partial pressures, oxygen, nitrogen, right? The pressure excreted by that single molecule of the gas mixture of the solution is partial pressure. Okay, so here we are talking about liquid in liquid solutions, and Raoult's law is also called as ideal solutions. It's much related to ideal solution. I'll tell you why that is much related to ideal solutions in a while. Before that, let's finish this Raoult's law. I said it is directly proportional to its mole fraction. Let's say I am counting it for total pressure, P total, which is equal to P1 plus P2. That is a partial pressure of one liquid and another liquid. In total, I'll get P total. Okay, so I know that the pressure, which is P1, that's proportional to its mole fraction, chi1, and its partial pressure of its pure solvent. Similarly, I can write it for P2, x2, P2 naught. So in total, I can write this as P1 naught, that is P1 which is equal to chi1 of P1 naught. P1 naught is, it represents the pressure of the pure solvent. Similarly, P2 is equal to chi2 of P2 naught. Here, delta H of the mixture, of delta H of mixing, which is equal to 0. Similarly, delta V of mixing, which is equal to 0. I said it is much related to its ideal solution. Why is it so? Because if a solution obeys these categories, these conditions, then that is called as ideal solution. And you know, there is no solution, is mostly all those solutions are non-ideal in nature. No other man in the world is ideal, right? So there are some imperfections in each and every human being or every living species in the world. It's not ideal. Similarly, the gases are also not ideal. But why we are talking about this? Because if we have certain rules, then we can see how much it is getting deviated. That's what we are going to talk about next. The deviations from the ideal solution. In case of ideal solutions, the AB interaction, AB, that is if I am having a molecule A and molecule B, the IAB interactions will be more or less equal to the interactions between A and B and B. Okay, so for example, if I am talking about a molecule which is a solution which is formed from A and B by forming an interaction between them, that is equal to, more or less that is equal to the interaction between AA molecules and AB molecules. That would be same, almost same. Okay, and you know that is not, there is no azeotropes formation in case of ideal solution, called as non-ideal solution. There are two types of deviations, positive deviation and negative deviation. What is positive deviation? In case of ideal solution, we have AB interaction which is more or less equal to AA interaction or BB interactions, right? But in case of non-ideal positive deviation, the AB interaction is less than the AA or BB interactions. For example, here you can see the famous example I have told you, ethanol in water or acetone in methanol. There are few other positive deviation non-ideal solutions also. I'll list down those in formula sheet. You can download it. Here I just took two examples, acetone in methanol. The AB interaction, the interaction between acetone and methanol, which is less when we are compared to acetone and acetone molecule, methanol and methanol molecule. Okay, and delta H mixing, which is greater than 0, and delta V mixing, that is also greater than 0, but in case of ideal, that is equal to 0, right? And Pi, which is greater than Pi naught into mole fraction of the solute. And these are forming minimum boiling azeotropes. But in case of ideal, there is no azeotropes formation. Here that is forming a minimum boiling azeotropes. By the figure, you can see what is positive deviation is. The dotted lines mention the ideal behavior, and the curves on the solid line, that indicates the vapor pressure of the solution, and you can see x1 which starts from 0 and ends with x1 is equal to 1, and x2 is equal to 1 and ended with x2 is equal to 0. The mole fraction I am mentioning. So it is more than, like, it is above the ideal solution plot. So this is positive deviation from the ideal behavior. Okay, so what about negative deviations? Negative deviation from ideal behavior is that just opposite to positive deviation, AB interaction will be more than that of AB or BB interactions, and delta H mixing and delta V mixing will be less than 0. But in case of positive deviations, it was more than 0. That means positive. Here that is negative. And also P1, which is less than P1 naught into chi. This forms maximum boiling azeotropes, but in case of positive, that is forming minimum boiling azeotropes. Here the examples are HCl in water, chloroform in acetone, and I'll be listing down more examples in the formula sheet. You can find that in description link. This is the picture of negative deviations. You can see this dotted lines are the ideal behavior and the solid line are non-ideal negative deviations. Then, now we have talked enough about solutions and how they are mixing. It's time to talk about their colligative properties. There are 4 important colligative properties. They are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. For each one of these, we do have a formula. These formulas are very important for solving the problems. So please note down this formula in your formula notebook and do the problems as much as you can related to this formula. So that this formula will not go away from your mind. Okay, so first let's start about relative lowering of vapor pressure. That deals with when the vapor pressure decreases while we are adding the solute to the solvent. For the dilute solutions, X naught represents the mole fraction of the solute, and the formula is P1 naught minus P1 divided by P1 naught, which is equal to N2. N represents number of moles. N1 and N2 represents number of moles of the components. The second colligative property, that is elevation in boiling point. Here we have a constant, that is boiling point elevation constant, that is ebullioscopic constant, you can also say, into molality. Kindly note this is molality, not molarity. So delta TB, how much the temperature difference you are observing. That is a change in temperature which is equal to boiling point elevation constant into molality. Then depression in freezing point. Here we have cryoscopic constant. That is dealing with how much of a temperature changes in your freezing point. So delta TF, which is equal to Kf into molality. And finally we have osmotic pressure. So osmotic pressure is represented by pi, which is equal to CRT. So CRT, R for gas constant, C for concentration, and T for temperature. The concentration you can find by number of moles by volume of the solution, that is also represented by N by V, that is molarity, isn't it? So you can also write for dilute solution pi is equal to mRT. Then comes 1/2 factor. You can expect questions from 1/2 factor. What is this factor? It is the ratio of experimental value of the colligative property to the calculated value of the colligative property. So sometimes, in most of the times in the reactions, we can't expect the theoretical value, right? So in that case, we came to the conclusion that is a 1/2 factor gives what is the change, what is the ratio for the observed colligative property versus calculated colligative property. This is denoted by the symbol I, and for the association reactions like Ag plus ion and Cl minus ion gives AgCl. In association reactions, I will be less than 1, and for dissociation, I is greater than 1. I can be calculated in several ways. It's just the proper ratio that is observed by calculated. You can calculate the I value by calculated molecular mass, by observed molecular mass, total number of moles of particles after association or dissociation divided by number of moles of particle before association and dissociation. Any which way you can find it out. How it affects the colligative property. Let's see the changes that is represented by the modified equations. Here you can see the elevation in boiling point delta Gb, which is equal to I into Kb into m. I factor, 1/2 factor, here you can have to include by calculating the temperature changes, freezing point, depression, or boiling point elevation, or osmotic pressure. Okay, sometimes the question can be asked from find out I from the given value. Here I want to tell you one more thing. In case of 1/2 factor and degree of dissociation, which is, we know that dissociation, which is represented by alpha, that is I minus 1 by n minus 1. Similarly, in case of association, taking out same symbol, that is alpha, which is equal to 1 minus I by 1 minus 1 by n. Okay, these two formulas are also important, so please note it down. Now it's time to solve some questions to sharpen our mind. Let's start with this problem, which is asking for a solution containing 6 grams of non-electrolyte solute in 200 grams of water. It has an osmotic pressure of 2.46 atm at 27 degrees Celsius. R value is given in liter atm. Our aim is to find molar mass of the solute. So problem is related to osmotic pressure. So what is the formula for osmotic pressure? Which is pi is equal to mRT, isn't it? So m stands for molarity, R for gas constant, T for temperature. So molarity, which is number of moles by volume of the solution. So number of moles we don't know because we have to find the molar mass. But we know number of moles, which is equal to mass by molecular mass or molar mass. So I am taking 6 divided by molar mass by volume, that is 200 grams of water. We know that density of water, which is 1 gram per ml, so which will be equal to 0.2 liters, right? Okay, so let's substitute everything in the formula, that is pi is equal to mRT. So pi value, which is given 2.46 m, that we don't know I'm taking it as 6 by mm into 0.2 liters into R value 0.082, temperature 27, so I have to take it as Kelvin. So 27 plus 273.15, so I'm taking that as 273 plus 27, which will become 300. So overall the answer becomes molar mass, which is equal to 300 divided by 2.46 into 0.2. So after doing the calculation, you will be ended up with 180 gram per mole. So that is the molar mass. So you can expect the same kind of question with other colligative properties as well. Okay, so let's move on to the second question, that is two liquids A and B form an ideal solution at 298 Kelvin. The vapor pressure of the pure A, that is 450 mmHg, and that of the pure B, that is 700 mmHg. Calculate the vapor pressure of solution containing 3 moles of A and 7 moles of B. So they have given the N values and P0 values as well. So let's work on it. They are asking for vapor pressure of the solution. So P total, which is equal to P A0 or 1 naught into XA or chi A plus P B0 into chi B. So what are the values we know? Number of moles of A and B. So chi A becomes 3 by 3 plus 7, that is 10, and chi B becomes 7 by 10. Similarly, PA0, that is pure A, 450 mm, and pure B, that is 700 mm. So just substitute the values. 3 by 10 plus 700 into 7 by 10. So which becomes, will get cancelled out, 45 into 3, and this will get cancelled out, 70 into 7. So in total you will get 625 mmHg. So that is the answer to this question. This question asks about a solution of glucose in water is in equilibrium with water and at 298 Kelvin. If the vapor pressure of the pure water at 298 Kelvin is 23.8 torr and the vapor pressure of the solution is 22.4 torr, calculate the molality. They are asking for vapor pressure and molality. So simply you can use the Raoult's law, which states that the vapor pressure of the pure solute minus the solution divided by pure solute. So which is equal to, of course, the mole fraction. So mole fraction of solute. Here that is glucose. So for example, I am substituting the values over here. P0, that is pure water, that is 23.8, and P, that is 22.4 divided by 23.8, which comes out to be the chi of solute, that is chi of glucose, mole fraction of glucose, which will be 0.0588, right? So once I found out the chi of glucose, I have to find the chi of water as well. So mole fraction of water, here they didn't mention about the volume. So in general, we are taking 1 kilogram as a volume. Why I am taking kilogram? Because they are asking for molarity. It's related to the kilograms, right? So per kilogram, what is moles of water? So N water, which is per kilogram, 1000 by 18, that is molecular weight, comes out to be 55.5 mole. Correct. So in that case, find out the N of glucose. We know that X of glucose, which is equal to N glucose divided by N water, mean number of moles of water plus number of moles of glucose. Just substitute the value 0.0588, which is equal to N glucose divided by 55.5 plus N glucose. So while solving this, you will be getting the N glucose to be 3.48 moles. What about molarity? Molarity is number of moles of solute divided by total weight in 1 kilogram of weight of a solution, right? Solvent. So in that case, which will be equal to 3.48, because we are taking it for per kilogram, right? So the answer to this question is 3.48 molar. Let's solve this problem, which is asking about the Henry's law constant for the solubility of N2 gas in water at 298 Kelvin is 1 into 10 to the power 5 atm. The mole fraction of N2 in air is 0.8. The number of moles of N2 from air dissolved in 10 moles of water at 298 Kelvin at 5 atm pressure. So let's analyze what are the informations we have. We have KH value, we have moles of N2. Do we have that? No, we do have mole fraction of N2, which is in air, that is 0.8, and number of moles of N2 from air dissolved into 10 moles of water, and the pressure is 5 atm. So this question deals with Dalton's law of partial pressure. In addition to that, we will come to Henry's law. So first, let's solve it. Let's find out the partial pressure of nitrogen gas. For that, partial pressure of nitrogen gas, which is equal to total pressure into mole fraction of N2, which comes to be 5 into 0.8. In total, that becomes 4, right? So now you can start substituting it in Henry's law, which states that P partial pressure, that is of N2, that is equal to KH into chi N2, right? So we do have a partial pressure value, that is 4, KH value, that is 1 into 10 to the power 5. So we will be entered up with the mole fraction of N2 will become 4 into 10 to the power minus 5, right? So in that case, let's consider the second part of the question, that is the moles of N2 from air dissolved in 10 moles of water. So number of moles of water is 10, so which makes the chi value of N2 that is number of moles of N2 plus number of moles of H2O. By substituting these values over here, we'll ended up with getting number of moles of N2. That is 4 into 10 to the power 5 plus 10 moles, which will be N2, that becomes 4 into 10 to the power minus 4. So option A, that is the right answer to this question. So if you are guys stuck with this part, so how to solve this and how to do the, do we have to go with the quadratic equation? No. How you can solve this part is that just multiply both the sides by the denominator, so that the denominator will get cancelled. You will be ended up with 10 to the power 5 into plus 10, which is equal to N2. So 4 into 10 to the power 5 N2 plus 4 into 10 to the power minus 4. Get the N2 on one side. So 1 minus 4 into 10 to the power minus 5 will become 0.99 N of N2. So N of N2, which is 4 into 10 to the power minus 4 divided by 0.99. So which becomes around 4 into 10 to the power minus 4. Okay, so let's move on to the next question, which is asking about a solution containing 4 grams of polyvinyl chloride polymer in 1 liter of dioxane was found to have a osmotic pressure of 4.1 into 10 to the power minus 4 atm at the temperature 27 degrees Celsius, that is equal to 300 Kelvin. Calculate the molecular weight of the polymer. Okay, so polymer is polyvinyl chloride here, and mass, that is 4 grams. So we know that the formula of osmotic pressure, that is mRT. So just substitute the values. Here molarity represents number of moles, which is mass by molecular mass. So I'm writing it as 4 by mm divided by the total volume, that is 1 liter. Then R value, that is 0.082, temperature 300. So I'm going to substitute the pi value as well, 4.1 into 10 to the power minus 4. So molecular mass goes here, 4.1 into 10 to the power minus 4 into 0.082 into 300. So it will be ended up getting 2.4 into 10 to the power 5. Option C is the right answer to this question. Let's move on to the next question, asking for when a 20 gram of naphthoic acid, that is C11H8O2, is dissolved in 50 grams of benzene, Kf value, that is 1.72, a freezing point depression, that is 2 Kelvin. Find the Van factor. So you can apply the Van factor along with the freezing point depression formula. So delta Tf, which is equal to cryoscopic constant. Before that, I have to put the Van factor Kf into molality. So which will be, this is 2I, that I have to find Kf 1.72, m molality that is 20 grams of naphthoic acid. So 20 mass by molecular mass. Molecular mass of naphthoic acid, that is 11 into 12, 8 into 1 and 2 into 16. So total you will be getting 172. 172 into the total mass, that is 50 grams. So grams into kilogram conversion, I am multiplying with 1000. So I value will become 2 into 172 into 50 divided by 1.72 into 20 into 1000. So it will get cancelled. It will be 20 and it will get cancelled. This will be of 100 times. So total 100 by 1 by 2, that is 0.5. Now let's move on to the next question, that is phenol dimerizes in benzene having the water factor 0.54. Okay, so find degree of association. I have given you the formula of degree of dissociation and association. So alpha, which is equal to 1 minus I into n by n minus 1. So 1 minus I, just substitute the I value over here, n, that becomes 2 because benzene is doing the association. So n value dimerizes as it mentioned. So 2 minus 1, which becomes 0.46 into 2, which is 0.92. So option D is the right answer to this question. Then, which of the following solution would exhibit abnormal qualitative properties? So this type of theory question can also be asked from this chapter. Here they are asking about abnormal colligative properties. Just think about the one thing, we are dealing with association and dissociation. So how many of the below molecules will undergo association or dissociation? Sucrose will not. Glucose, no. What about glass powder in water? Obviously not. So the right answer is 0.1 molar NaCl. So with this we come to the end of this session. I have solved many problems in many concepts. So if you want any other problems to be solved, please let us know in the comment section below and keep practicing so that you will get an idea what kind of questions they can be asked. Theory part is not alone enough to practice. That is much more important because practice makes a man perfect. Thank you.